As I mentioned in the previous video, we're not going to do much more or any more at all with the beta distribution in this course, but it is certainly an important distribution. You should be aware of it, and the beta function is also of interest in its own right, and it can also be used to solve integrals, not just integrals over the unit interval. Sometimes by making substitutions for x in here, we can solve other integrals very quickly and nicely using the fact that beta of alpha beta is this product and quotient of gamma functions. Here's a nice little lemma for you. Lemma. If alpha and beta are numbers bigger than 0, then the integral from 0 to infinity of y to the alpha minus 1 over 1 plus y to the alpha plus beta dy turns out to be just the beta function evaluated at alpha and beta, which of course we know is gamma of alpha times gamma of beta all over gamma of alpha plus beta, which can be very easy to evaluate if alpha and beta are integers, or non-negative integers, right? Of course they're not negative. Okay, so let's prove this nice little result. So here's the proof. So first of all, let's set x equal to y over 1 plus y. I'll use that as my substitution. Then this implies that 1 minus x is 1 over 1 plus y, right? Okay, so I'll remember that. I remember this, and I remember this. Now I'm going to need to get an expression for dx also, right? So if I'd say dx dy, if I differentiate that way, that's going to be, let's say, using the product rule here on this guy. See, this is a product of y and 1 over 1 plus y. This is just going to be 1 plus y, 1 over 1 plus y, right? Plus, let's see, y times the derivative of 1 over 1 plus y is, take 1 plus y to the negative 2th, and then times a negative 1, right? And so this actually just works out to be 1 over 1 plus y minus, let's see, y over 1 plus y squared. And I can combine those terms into just, let's see, if I multiply top and bottom by 1, oops, sorry, missing some parentheses there. If I multiply top and bottom here by 1 plus y, I get 1 plus y in the top, minus a y. It's just 1 over 1 plus y quantity squared. And so this means that dx is this stuff times dy, right? I can get rid of this. I can multiply through by dy effectively, right? So write that down. I'll have that dx is dy over 1 plus y quantity squared. Okay. So this means that I can rewrite that beta function, beta of alpha and beta, rather, is the integral. I'm not going to fill in my limits yet. I'm going to wait a second on those. Remember, x is y over 1 plus y. Remember what we're doing here. I'm starting with the way the beta function is usually written, like this, and I'm making that substitution. X is y over 1 plus y. X is y over 1 plus y. Sticking that in there, and then sticking it in there. Right? Okay. So x is y over 1 plus y. This is being raised to the alpha minus 1. And then 1 minus x, that turns out to be 1 over 1 plus y, all that's going to be raised to the beta minus 1. And then my dx part, remember we worked so hard on that up here, it's dy over 1 plus y quantity squared. Okay, now we need to make sure that we get these limits correct. So what happens is x goes to 1 or as x goes to 0, right? Over here, these are the limits of integration, right? So as x goes down to 0, what's happening to y? X goes to 0 as y goes to 0, and vice versa, right? So y goes to 0. Now what happens as x goes to 1? How can you get x going to 1? X is going to go to 1 as y goes to infinity, right? Okay, so means y goes to infinity, like that. So really, I'm going to change my limits of integration to look like that. Now I can simplify this, the integrand here a little bit. This is in here. I'll take let's see. This will be y to the alpha minus 1 times 1 plus y. Right? I've got a bunch of 1 plus y factors. Here I've got 1 plus y raised to the 1 minus alpha, and then here I've got it raised to the 1 minus beta, and here I've got it raised to the negative 2th, right? dy. So 1 plus 1 minus 2 is 0. This just works out to be the integral from 0 to infinity of y to the alpha minus 1 over 1 plus y raised to the alpha plus beta dy. Okay? Now, good. So all of this is equal to the beta function evaluated at alpha beta, right? So by the way, our limit is proven, right? This is done. And because we already know that the beta function, beta of alpha beta, is gamma of alpha times gamma of beta all over gamma of alpha plus beta, we know that we can, if we see an integral that looks like this, and we can quickly solve it if we know the values of gamma of alpha and gamma of beta and gamma of alpha plus beta. It's especially quick if these guys are integers, because the gamma function is results to the factorial function, right? So for example, if I bump into an integral along the way that looks like this, right? How do you solve this? Maybe you want to pause the video here and take a stab at that. Okay. Well, let's see. Alpha minus 1 is this. So that means alpha is 4, right? This is going to be gamma of 4 times, let's see, 5 is alpha plus beta. Alpha is 4, so beta is 1. This stuff down here, this is gamma of 4 plus 1, right? Gamma of 1, right? Because these guys are integers, remember gamma of n, gamma of an integer n is n minus 1 factorial. So this will be 3 factorial times 0 factorial over 4 factorial, which is 6, right, over 24. It's a quarter. Good job. Maybe you want to remember this result. Maybe you'll have it on a quiz. Maybe so.